Newton's second law of motion for matter. Newton's first law leads into Newton's second. It's kind of an obvious extension. If all the forces on an object are balanced, it's either going to sit there, or if it's moving, it'll never decrease speed. It'll never increase speed, it'll never turn. Until what? That is, how do you make something increase speed, get moving, decrease speed, or turn? What causes that? And we want things that we can measure. So it's not fuzzy. This is measurable. There's an amount. You can measure how much the spring stretches to exert a force, and twice the stretch, twice the force kind of thing, but it's a lot of detail work. But you know, again, thinking in the text, I've got that example, think it through, look at the solutions, read it through. When it clicks, it clicks. You still will likely get tricked, as physics students do, until you retrain your awareness. But think of a kid on a skateboard, a very smooth path, and an elephant on a skateboard, for example. Just as an extreme. Of course, you can have an adult and a little kid, whatever. So how do you make something increase speed or stop it, decrease speed, or turn? It's coming towards you. Sliding in the hockey rink, going, I gotta stop that. It's out of control. What is it? Oh, it's a kid. Oh, okay, no problem. What is it? Oh, it's a offensive lineman for the whatever team you like. Hard to stop them. Coming the same speed. I'll take the kid. You take the offensive tackle. All right. So what do you have to do? You got to exert a force against the motion, right? In fact, we're going to talk about this. And unbalanced forces, unbalanced. Sometimes you call them the net force. The total force is another. Right? When you add up all the forces, if the forces are not balanced, then that will cause acceleration, and you know what the acceleration is. Again, I hope you have your book open and you kind of look that over, look at this, and think about this. So, increase speed, decrease speed, or turn. Again, key for orbiting things. All right, so why is something increasing speed? There's got to be an unbalanced force, or force is, on it. Why is it going to decrease speed? There's got to be someone to blame, something, some other object. Why is it turning? There's got to be something to blame. That's going to be huge. Okay. Now let me say this a little bit. If the unbalanced force is in the direction that something is moving, what do you think will happen? Something on skateboard. If the unbalanced force is this way, of course it'll increase speed. And so there's an intuition that works, and then you get tricked. What if it's moving and the unbalanced force is opposite the motion? It'll decrease speed. And what if you push to the side? It'll turn. Or pull it to the side, it'll turn. If I pull it this way, it's going to turn that way. If I push it that way, it'll turn that way. That's the idea. That's all you need, is just that conceptual, but keeping this straight. And remember that this will never stop on its own. Right? It'll never get going on its own. Something else has to be to blame. It'll never turn on its own. Okay? It'll never go around a corner on its own. Now, if the unbalanced force is stronger, you push harder, a stronger unbalanced force, this way, or that way, then what do you get? Turn, put that up there. You get more acceleration. What does more acceleration mean? More abrupt, right? Slam on the gas, slam on the brakes, crank the steering wheel. So, abrupt. And you can flip it, of course, a weaker unbalanced force with less acceleration and more gentle. But there's a difference, right? You could push the same on the kid on the skateboard and the elephant on the skateboard, or whatever it is. Try playing catch with this. Ugh. This is fine. Problem. So it depends on what the object is. And what property does that object have? Mass. Inertia. Resistance to accelerate. So if it's got more mass, the more mass it has, the more inertia it has, and the more gravity. Okay. But the more mass the object has, you push the same on the kid, take off. Do that to the elephant. Right. More mass. So there's these different factors, and that's what's kind of tricky about this, right? Let's take a little quick look at that. I'll demonstrate that a little bit, and then you just go push people around. And you go, huh, oh, you don't have much mass. Huh, oh, you do have a lot of mass. See ya. Not necessarily, whatever. So that's it. So notice this is if it's balanced, they keep on going. That's the surprise. This is not so surprising. You push harder, you're going to get more abrupt change. But you can push with the motion, opposite the motion, or to the side. Stronger force, more abrupt. But it depends on how much mass that thing has. And I want to point something out in a moment. Okay, so let's take a look here. Now I'm going to measure how much force I have by how much the spring stretches. And you'll be able to visually kind of roughly see, how far could I go? I can go out to here. You can roughly see whether it's a more gentle or more abrupt acceleration. So, I'm going to stretch the spring out to red. And I'm going to give it a certain force. Let's see. You're really having trouble keeping your head straight. We're on. Okay. Pretty abrupt acceleration, right? All right. Now what if you got more mass? More abrupt or more gentle? I'm going to have the same force. Why? Because I'm going to stretch the spring the same. You can imagine really loading it up. And if you took measurements of time and distance and all that stuff, you can figure out how much. We're not doing that. How does that work for decreasing speed? Well, if I get it going, the spring doesn't have to stretch much to stop it and get it going back the other way, right? Get that going? Good luck stopping it. I gotta really stretch the spring a lot to stop that one. Very gentle acceleration. Why? Because there's a lot of resistance to change. It's true too with turning. If it's got more mass, it's harder to increase speed, decrease speed, or turn. What's going to make it increase speed, decrease speed, or turn is an unbalanced force. More force is going to give it more acceleration, more abrupt. That's Newton's second law. Now I'll say two things. Let's see where we are. And that'll be it until we drill this a little bit. Okay. One, you will see this written mathematically. We're not doing calculations in this class. It's descriptive. You can think you can get more out of it without that. If you're comfortable with it, fine. You can calculate it. This is, it says, may that be with you. This is force, you can imagine. This is mass. this is the change in velocity, and the change, if I have more change in velocity, this whole thing is acceleration. More change in velocity is more acceleration. More force, more acceleration. Less change, less acceleration. If you change the same amount, if you change it more abruptly, less time, if this number is smaller, that makes this bigger acceleration. If this number is bigger, more time to change to get up to speed or to slow down. This is bigger, this whole thing is smaller. You don't have to follow that. Also, two things, and then I'll give you my pet peeve on two things here. One is this little sign means that there's a direction to these things. Mass doesn't have direction, but these have direction. It's called vectors. And the writing acceleration like this uses calculus. Guess who invented calculus? Newton. Man, what a dude. I mean, seriously. Some say he was a little cranky, but Galileo was probably more fun to hang out with. But also a guy named Leibniz, this German guy that there's a question of who did it first, etc. But Galileo wanted to, Newton wanted to explain this stuff, and he worked with the mathematics. So to do astronomy, yeah, you got to get into the math and the physics in this, but you also need to have a clear understanding. And so one thing, this is force. This is the push or pull. This is what happens. This is not a force. So when it says, may this force be with you, yes. If I see things like that, may this be with you, okay, you can just ignore me, but that's not force. That's what happens because I know they're equal. You could have the same money in your bank account as I do. It doesn't mean I get to draw money from your account. They can be equal. That's what this says. They're the same amount, in this case, same direction too. But they're not the same thing. This is the pushes and pulls coming from things. Anyway, forget about that. Don't worry. But don't. It's really may the force be with you. Okay, so one more little thing. It's kind of a big thing. This is tricky. And so people, you fall into just repeating the words, but try to see it. And if you think about it, where does mass come into play? It comes into play as inertia right here. More mass, less acceleration. Less mass, more acceleration. Does this depend on mass? This could be the kid. This could be a ping pong ball. This could be an elephant, a truck, a motorcycle, whatever. This is completely independent of mass. It is completely, nothing was said here about mass. Nothing. It doesn't matter the mass. It doesn't matter the inertia. You're not changing. So it doesn't need to resist. All things will do this. There's no resisting. There's no resisting until there's an unbalanced force. So this is, I'm trying to change this, but for now, always, I've never yet, but called the law of inertia. It's the law of equilibrium, the law of balance. We can correct things, we can improve things, we can think more clearly. The law of equilibrium, no matter what your mass is. Here it makes a difference. More mass is harder to accelerate. How are you gonna, what are you trying to, you're trying to accelerate it by pushing, pulling, whatever. That's it. You saw that. We'll get to that. Astronomy, and I think we did calculus, a little bit of that. It's learnable. It's just, takes time, takes an investment. It's worth it if you like it. And got it? Examples, I think you've got plenty of examples in the text. Read the text, think about that. And here, one more, turning. Grab a little kid by the arms and swing him around, right? It's fun, just be careful. Right, so now grab that offensive lineman by the arms, and it's harder to do, right? For various reasons. So mass does come into play when you're trying to increase speed, decrease speed, or here, not here. Things do this. if they're left alone or all the forces are balanced. You gotta make them. Let's try it out.